So thanks, everyone. This is going to be a very interesting talk because instead of a review, it's more like a preview because we don't have yet a lot of clustering measurements from James Webb, although definitely there have been groups who've started up that work. And so this is more of saying, what can we learn from James Webb? How should we be thinking about proposals for future cycles, including cycle 4? And so how can we use this amazing new instrument to learn more about galaxies and black holes? Okay, and so just as a quick motivation, why bother? Why bother thinking about clustering of galaxies and supermassive black holes? Well, here I have just all the components that we usually think about: halo, gas, galaxy, and supermassive black holes. And I've drawn some arrows now for every physical process that links the four of these things together. And what you'll notice is that there's an arrow connecting everything to everything else in both directions. And so literally, if we don't think about what the halo is doing to the gas in the galaxy and the supermassive black hole, then we're sort of ignoring the effects of half of the physical processes at play in shaping galaxies and supermassive black holes. So there's actually a lot that we can learn about what is the halo doing. Just as a practical example of this, connecting sort of supermassive black holes to other things, including the halo, we often see supermassive black hole talks where people find massive black holes at early redshifts, like redshift 7 and 6, that are overmassive. And the question is always sort of, how do we grow these massive black holes if we're limited to the Eddington rate of growth? And that's sort of a question that's focused on what is a supermassive black hole doing. If we step out a little bit and talk about what is the host galaxy doing or the host halo doing, then what we find is that typical growth rates for the galaxy is shown here in red, or the host halo is shown here in blue, end up being much, much higher at earlier times, such that typical galaxies grow at the Eddington limit for black holes above redshift 10. So in fact, the question is not sort of, how does the galaxy know about the Eddington limit? Already, because of lambda CDM, the galaxy and the host halo know something about high specific growth rates at early times. The question is more, how do we get the gas from the galaxy scale down to the black hole scale, maintaining at the same specific growth rate? Okay. Next sort of point of motivation is sort of, why do we care about using James Webb to say anything about galaxy or AGN clustering or environments? Here's a plot showing the relative clustering compared to dark matter for halos of different masses. This is on large scale, so this is effectively the bias squared. If we look at redshift 0, what we see is actually very, very little difference in clustering until you get to above the collapse mass, which is around 10 to the 12 point something. So you're only really sensitive to halo masses on groupish to clusterish scales from looking at the environment. If you go to higher redshifts, though, the picture changes completely, because as you go to higher and higher redshifts, the collapse mass gets smaller and smaller and smaller. And so the inflection point of this bias halo mass scaling goes to lower and lower halo masses, such that everything that you can observe is in this sort of hockey stick exponential growth region at higher redshifts. So in contrast to the situation at low redshifts, once you're sort of above redshift 4, almost everything that you can see is actually going to have a very strong dependence of its clustering, its nearby environment, with halo mass. And I realize this is a theory-centric measure, the halo mass. If I convert this to an observational-centric measure, the, say, more observational-centric measure, like the stellar mass, this is sort of the range of stellar masses you might be expect to be able to see with something like James Webb. And you can see that above redshift 4, you have very strong dependencies of clustering with stellar mass as well. So in other words, the host halo properties you can actually get by looking at the environment in a very effective way, even for low mass things, in a way that you could not do at redshift 0, but at redshift greater than 4, this is possible. Okay. So now that I've done a little bit of motivation, why do we care about clustering or environments of galaxies and black holes at high redshifts? Let's go back to some basics to understand what can we learn from this. So if I look at a basic plot of clustering, so this is a galaxy autocorrelation function, you can sort of look at any of thousands of different papers that have measured this or predicted this from theoretical models. We usually talk about two regimes, a one halo term and a two halo term. The one halo term is mostly contributed by galaxies within the same dark matter halo, and then the two halo term is contributed by from galaxies in different dark matter halos. We often talk about the one halo term being mostly influenced by the satellite fractions. So for instance, quiescent versus star-forming galaxies have different fractions as satellites versus central galaxies, contributing to a large difference in the one halo term. And then on larger scales, we see differences in the characteristic host halo masses. In contrast, I want to be a little bit careful about language because often we say, just as I did, incorrectly, differences in host halo masses. Actually, characteristic halo mass is a better description because a difference out on large scales here can correspond to either your host halo being different or being a satellite of a different mass host halo or orbiting around a different mass large halo. So in other words, it's just to say that your environment looks like the environment of massive halos or low mass halos, depending on the bias on the large scales here. Okay. So what can we learn from looking at clustering on small and large scales? Generically, we learn about the host halo masses, and there have been a number of papers that have either predicted clustering using Mach catalog type things. So Aaron has had a paper on this, and Chris gave a great overview earlier this week about all the simulations that have been done at high redshifts. And so all of those in principle have an effective Mach catalog that you can get clustering out of. This particular plot is from a paper by Ryan Ensley, where he tried to mock up the JADES observations and ask how well could you recover halo masses by both spectroscopy, so that's redshift 4 to redshift 6, and then do photometric clustering from redshift 7 to redshift 10. And the answer was you could get quite good constraints on clustering as a function of absolute UV magnitude and measure a strong change between, say, redshift 4 and redshift 10 in the clustering of galaxies at fixed UV magnitude. Of course, now we have James Webb. We actually can do observations of this. I'll leave it to Mark to talk more about what the observations have done, but actually people have done this and you can see constraints already populating the space. Okay. Another fun thing is that not only can you get halo masses, but you also might be able to get better stellar masses too. And so for some classes of objects, you might have very large uncertainties in stellar masses. And the classical example of that is little red dots. And so we've heard from some speakers earlier this week and early in the program too, that depending on sort of which templates you use, which AGN templates, which stellar fitting templates you get, because the SEDs of little red dots are so weird, you can get sort of plus or minus a dex of error or uncertainty either way in saying what are the stellar masses. And if you care about what are the implications for little red dots in terms of the black hole mass bulge mass or black hole mass stellar mass relationships, that's a sort of huge uncertainty that you'd want to reduce. And so if you look at the clustering around those things and get at their host halo masses, the stellar mass halo mass relationship is tight enough that you would actually get better constraints on their stellar masses just from looking at the clustering and applying a stellar mass halo mass relationship to that inferred halo mass. So that's just a fun thought to throw out there, and perhaps people are already working on this. The other thing that you can get is burstiness. So we've heard a lot of talk about burstiness. Also, AGN folk like to think about duty cycles, which is basically the same thing. The idea here is that there is a joint constraint from number densities and from clustering. And so the thought here is that if you have a very smooth accretion rate or a constant output, then the brightest things will live in the most massive halos, and you will get a very high clustering for the brightest things. If you have a lot of burstiness, however, then you have a lot of low mass halos that can sort of briefly burst up to higher luminosities. And so then you have, on average, a lower bias. And so I just wanted to give a shout out to Julian here, for making some predictions about what James Webb, as well as other high redshift experiments, could get for constraining burstiness in galaxies using clustering. So the thought is that if you have a constant efficiency versus a high scatter, then you can get different constraints for the same number densities by looking at the different clustering of the neighbors around. Okay. And then the last sort of thing that is low-hanging fruit is just pair fractions, which tells you about things like merger rates. And so again, depending on the redshift range you're interested in, the constraints from spectroscopic observations of galaxies give you really nice constraints on merger rates for galaxies. And again, comparison with simulations that tells you about how do galaxies disrupt as they get closer and closer to each other. Okay. So let me pause there and just give you a moment to process. So there's a lot of low-hanging fruit just from looking at the environments of galaxies, burstiness, pair fractions, as well as more standard things like halo masses and stellar masses. Good. So moving onward, there are more and more fun things that can be done. So one area of, well, where do you go after the low-hanging fruit is differential clustering. And so this is sort of an underexplored area, not just at high redshift, but also at low redshift. So there have been tons and tons of papers pointing out the fact that quenched galaxies cluster differently from star-forming galaxies. But it's not just sort of quenched versus star-forming. No matter what property of a galaxy you split on, you can often find some differences in the relationship with environment. So one example, I mean, there have been tons of examples that we've discussed in the past, like morphology density relations, color density relations, AGN, like type 1 versus type 2. But also, there's sort of been, in recent years, a resurgence in interest in again splitting galaxies by different properties to see what kinds of effects can we measure. And the basic story is that if you find a difference in clustering when you split galaxies in a certain way, then you know that has to correlate with some sort of long timescale process as opposed to a stochastic process that just is sort of within the galaxy and doesn't correlate with the halo. Because clustering differences are inherited from what the host halo is doing, basically. Whereas if you have a stochastic process that's just within the galaxy that is uncorrelated with what the host halo is doing, then you shouldn't see any clustering differences when you split galaxies on that property. So for example, one fun thing that you can do is split galaxies by sizes. This is something that I've done and others have been interested in too. If you split galaxies by sizes at low redshift, you find clustering differences. So if you take a bin of stellar mass, you split galaxies into large physical size versus small physical size, you compare their clustering, you find that large galaxies have lower clustering than small galaxies. And you can actually then ask, do models of galaxy sizes reproduce the observed clustering or do they not? The summary is that the spin times halo radius traditional model does not match the actual clustering of galaxies. So you actually learn something about the physical processes that set galaxy sizes by looking at differential clustering. This is not a unique thing to galaxy sizes or morphologies or type 1 versus type 2 AGN. I'm just going to very, very briefly mention the words assembly bias and secondary bias, where if you look carefully at the shape of the correlation function, that can actually tell you about a lot of different things that are happening inside halos. And different models for how galaxies correlate with their halo properties will give you very different differential clustering results. So I'll just gloss over that whole field of inquiry and just say that there are just a huge number of things that we could split galaxies on at fixed mass, like size, bulge to disk ratio, metallicity, specific star formation rates, colors, clumpiness, line ratios, AGN luminosities, line widths. And so the thought here is just that there's a whole sort of field of science waiting to happen if we split galaxies on all these different properties and look, how do they cluster differently? Because how they cluster differently is something we can very easily measure in simulations and in the observations. And then we learn something because every time you have an easy comparison between simulations and observations, you learn something new. Okay. I'm going to then take a few minutes to talk about sort of advances in the theory of thinking about the information content in environment. So one thing that you'll notice with clustering is that even sort of things that we would consider typical galaxies at high redshifts are actually in extremely biased environments. And so if you find, say, one extra galaxy that is at a high stellar mass, then that will cause a strong bias to the stellar mass function or luminosity function because it's in such a clustered environment that it will have a whole bunch of other things nearby. And that means that actually clustering is one of the noisier measures of environment that you can invent. There are other types of measures that are less noisy and perhaps more informative than clustering. One example of this is counts in cells. So I just want to briefly mention some basics about counts in cells so that folks have a broader understanding because we often don't talk about it in graduate classes. So if you think about counts in cells, what do I mean by counts in cells? I mean just if you have a survey, you randomly pick points in that survey, and then you count how many galaxies are in apertures of a certain projected distance. And then you plot the probability distribution of those counts in those apertures. So it also goes by counts in annuli, counts in cells, different names for it. So if you just had a random distribution of galaxies across the sky, no clustering, just purely independently throw down galaxies, you might get a distribution that looks like this. If you then have a biased distribution of galaxies, like those that might live in halos of a given mass, then you'll see some sort of cells that have a lot of galaxies in them, reflecting the fact that they're clustered, and then some cells that have almost no galaxies in them, reflecting the fact that you sort of have to maintain the same number density as sort of this distribution over here. If you had a population that lived in a higher halo mass, so this might be, say, just taking a delta function of halo mass and populating all those halos with galaxies. If you had something that lived in a higher halo mass sample, then you'd have a lower number density and you'd have increased clustering for some cells and then decreased clustering down here for some cells. So in other words, you'd have a wider spread as well as sort of a higher average clustering here. But it's not just sort of what is the characteristic halo mass that you can get at, but also the scatter, because if you increase the scatter in the distribution of host halo masses, you would also increase the scatter in the distribution of counts in cells, right? So there's actually a lot of information in the overall shape of this counts in cells distribution, which is lost in something like a correlation function where you weight by source counts. So counts in cells is one sort of promising new method for thinking about not only what is the characteristic halo mass, but simultaneously what is the scatter, what is the duty cycle, and all of that together. So sort of full recovery of the distribution of host halo masses in a possibly less noisy way than a clustering function that's weighted towards the most biased galaxies. Okay. And even sort of further in the future, thinking about this is field level inference. And so the idea here is that, okay, well, these are things like counts in cells and clustering that humans thought might be interesting, but there's even more information potentially in the higher order moments of the distribution of galaxies. And how can we extract that? Well, the thought is, okay, if we just list all the information that a distribution of galaxies might have, so things like magnitudes and distances to other galaxies, if we just throw all of that into a huge vector, input vector for a neural network, then we can train that neural network on the simulation to get out sort of any property that we want, like a halo mass or a halo growth rate or sort of anything else. And in this way, we can use both the power of lambda CDM simulations as well as all the information from observations to get out lots of different properties, lots of different information that we might otherwise have been unable to do. So I just very briefly want to mention that there are a lot of folks interested in applying this at Redshift 0, where you have a lot higher density of spectra, but in the future, we'd also like to do this thinking forward to beyond James Webb to wide area spectroscopic samples at high redshift. So
Peter, you
yeah,
have 5 minutes.
great.
Yes.
I'm gonna say actually I'm done. I'll just put up a summary here. So
Okay.
main main thoughts. The low-hanging fruit that we can get from observations, things like galaxy AGN characteristic host masses, host halo masses, stellar masses when it's hard to do SEV fitting, satellite fractions, burstiness or duty cycles, all of this can be done either now or soon with James Webb. To help with that, there are lots of catalogs. I've done one, Aaron has done one. A lot of simulators have created catalogs and light cones that are available to help you with planning for proposals. Cycle 4 is due soon, of course. And in the future, I'm really excited about the potential of differential clustering by different AGN, different galaxy properties, to get at what are the physical mechanisms driving how galaxies appear the way that they do. And then in the farther future, of course, we'll have even better ways of measuring clustering, even better ways of measuring environment to maximize the amount of information we can extract from a sort of limited amount of spectra that we can take at high redshift. So thank you all, and I'm happy to have more time for questions to talk about any of this.
Absolutely. Thank you very much, Peter. Okay, if you can have questions for Peter, please say your name before.
Hi, Peter, it's Marta. I want to ask a clarification on something that perhaps I misunderstood. So you showed that burstiness affects clustering
Yes.
if galaxies are scattered. But then you said, when talking about selecting different samples, that stochastic processes don't affect clustering.
Oh, great.
So I'm confused about this. Can you?
Great.
Thank
Yeah.
you.
So I think the difference is clustering overall versus differential clustering. Okay, so if you have a bursty process that happens sort of at random, what that means is that lower mass halos can contribute to higher luminosity objects. And so if your average or characteristic host halo is lower mass, then that will change the bias that you observe. Then if we switch to talking about, let's look at an entire sample and just, or sort of a sample which, right, so the differential clustering example is sort of, let's take a sample with in a fixed bin of stellar mass. And the reason to choose a fixed bin of stellar mass is that as far as we know, stellar mass seems to be correlated with halo mass and not that much else. So that if you have a fair sample in stellar masses now you can split by those which are sort of high luminosity or low luminosity, or in some other way. So you can say, okay, is the luminosity of the galaxy now within this bin of stellar mass, which I think corresponds to a bin of halo mass, does the luminosity seem to correlate with clustering in some way? And if you now are selecting just galaxies within a bin of stellar mass or approximately a bin of halo mass, then the question takes on a different meaning compared to, is there a difference between the clustering that you expect from the given number density of the galaxies? Does that help answer your question, or should I say it again in a different way so that, because I feel
Marta says yes, so she's happy. Okay, let's continue in this order.
Hey, Peter, Joe Hanawi here. Thanks for a great talk. Definitely preaching to the choir about the usefulness of clustering. And I'll say JWST is a clustering machine. I found your discussion, just mainly a comment, I found your discussion of beyond clustering a little bit misleading. So, right, if you're dealing with, if you're working on linear scales, basically galaxies are Gaussian random field, and so the correlation function is basically an optimal estimator for everything. It contains all of the information. So what you're really talking about, going beyond the correlation function, is you're really talking about extracting nonlinear information. I think that's a better way to phrase it than to talk about counts and cells, because if I do counts and cells on large scales, there's no new information there. But I guess the thing I wanted to get your feedback on is, as you know, working on nonlinear scales involves subhalos, things like, rock star, all the things that you've thought more about than anybody else. So maybe you could or many in the room, maybe you could let us know what you think the challenges are there.
Yeah, so there are a couple things. So just as going back to this sort of basic clustering picture, we talk about sort of one halo being the satellites, two halos being sort of things far apart from each other. The story is actually a little bit more complicated because every time you have a change in slope, that corresponds to a different physical process that starts to matter. And so if you go on large scales and you see a change in slope here to smaller scales, and that's telling you that so suddenly nonlinear motions, satellites and angular momentum barriers are starting to be important. But then you see another change in slope down here on smaller scales. And what that is telling you is that somehow there's another physical process coming in, which could be things like tidal disruption of satellites and so on, that's again sort of flattening the slope to make it look more like that one on large scales. So the sort of exact shape of the correlation function overall is telling you something about what are the satellites doing. And that lets you constrain sort of in your simulations, what is the disruption rate of satellites that you need to sort of match the overall clustering. Once you then do differential clustering, that tells you information beyond what the satellites are doing, and you can then extract other processes. So in other words, there's a very interesting question about how soon do satellites disrupt? Are n-body simulations getting the right answers for those, or are they not? But you can often get at those questions by looking at the all clustering or the cross-correlation of mass-selected samples. And then once you have a model that reproduces the all clustering of the cross-correlation of mass-selected samples, then you can start learning more cool things about the differential clustering of different halo properties. So I'm happy to talk about the details of how you would actually end up doing this, but that's sort of the overall picture, is that there's enough information in the data to both constrain what are the satellites doing as well as beyond what are the satellites doing.
Okay, we have another question from Aklant, and then
Hi, Peter. Thanks for a great talk. This is Aklant. So we know that at high redshift, kind of related to what you were saying earlier, that nonlinear bias, even in the two halo regime, becomes increasingly important, significant at higher and higher redshifts. So how much challenge does that pose in being able to target the linear regime and constrain the linear bias of these galaxies, especially in like JWST, which is not the largest survey?
I'm a little bit confused by your question, actually, because the nonlinear regime, I mean, yes, there's nonlinear bias around sort of massive things, but it doesn't necessarily extend a lot further out, because sort of where do you have the 1 to 2 halo transition? I mean, it still happens around this same point, and so you effectively have on large scales very little sort of things you can do with the bias to make it not just telling you about a characteristic halo mass. Another way of phrasing that is if you look, for example, at any other secondary bias and how it depends on distance, at high redshifts, you see all of these things flatten out. And so on scales beyond sort of 4-ish, 5-ish projected MPC, then you have very little change in the clustering that could be due to sort of nonlinear type things.
Okay, so Julian and
Hey, Peter, it's Julian. Great talk. Thank you for the review. I want to ask you the question that you don't want to be asked about assembly bias.
Great.
What do we do with it? Is it going to be worse at high redshift, at low redshift? Do you have any idea? Is it going to make it hard or impossible to measure halo masses? What do you think?
Great. So assembly bias, so I think it becomes somewhat less major of an issue at higher redshifts just because of how steep the dependence on halo mass becomes. And so where does assembly bias or secondary bias hurt you? It hurts you if you have, for example, like a lot of things in satellites around more massive halos or orbiting around more massive halos. So you have to be a little bit careful about the interpretation, and it's helpful to look at sort of the distribution of masses of nearby things. So is it just that you're close to massive galaxies, but your galaxy itself is not that massive? That's a different story than, yes, my host galaxy is also massive and it looks like it's in a very dense environment too. So that's sort of the only thing that can mess you up at high redshifts when your dependence of clustering on halo mass is so steep like this.
So you're saying the bias is so large that we can kind of forget about it, assuming it's additive and not multiplicative.
Not that secondary bias isn't there, but the effects from the bias as a function of halo mass, I think, are so much larger that to first order you might not care as much as you do at low redshifts, where sort of for galaxies and halos in this low mass range, basically all of the clustering differences you see are going to be from secondary bias.
Okay, cool.
Great.
Thanks for a great talk, Peter. Just a quick comment to Joe's point. In work led by Christian Jesperson, actually using universe machine mock catalogs, we showed that the counts and cells distribution does have significant skewness and kurtosis on the scale of the JWST fields that we currently have. So you might not guess that because you might think it's so early, there's been no time for that non-Gaussianity to develop. But because of the effects that Peter has been mentioning, you do actually have significant higher order information beyond the correlation function. So I completely agree that, you know, something like counts and cells or whatever your favorite, you know, way of capturing that additional information is going to be interesting. But Peter, I actually wanted to ask you a different, somewhat more practical question, and that is, as you know, I'm a huge fan of these kinds of tests, but I'm worried that once you start, you know, binning things by stellar mass and then dividing into some secondary characteristic, that with the samples we may have in the near future with JWST, that our statistics are just going to be too low. So are there ways around that by using marked correlation statistics, or maybe there's something fancy we can do with field level? What are your thoughts on that?
Great. Yeah, so marked correlation functions are interesting. It's a little bit dangerous to mark on the actual property because you could be influenced by outliers in strange ways. So if you can mark by sort of rank order in something, like specific star formation or stellar mass, then that is interesting. I think, however, that with some of the samples that we'll get, it's still possible to just do direct split clustering. So for example, the Capers program, which I think Mark will be telling us a lot more about, I think that has enough sample size that you could actually see clustering differences between different samples. It might be only at lower redshifts like redshifts 4, 5, and 6, but compared to the past where we had no information beyond redshift 1, I think that's still a huge improvement.
Okay, we have time.
So, yeah.
Are you
Yeah,
done?
so
Okay.
yeah, I just want to say marked correlation functions could be a solution. On the other hand, I think there's a lot of motivation in getting large enough samples to do split correlation functions that because of all the information you can learn about the connection with the host halo and the long versus short potential duration of the physical processes, that yeah, like I think TACS might be interested to give us larger samples. So
Okay, we have time for just a short question and a short answer. Well, Crystal, can you please set up?
Hi, Peter. This is Jake Helton. Thank you for the talk. You mentioned low-hanging fruit that people haven't done with JWST. Could you comment on what you might think is the most impactful thing that you haven't seen or you haven't seen a lot of?
sure. I think the first point here is my summary of what low-hanging fruit is there. I've only seen sort of one paper on UV correlation functions. And so the natural next step would be stellar mass functions, or sorry, stellar mass halo mass relations. And of course, we also have some early results that I hope Mark will talk about from Aspire and Eiger about sort of what are the environments around high redshift quasars. But then also, of course, it's interesting to consider environments around little red dots just to say what are the stellar masses. So I think there's a lot in here that is already available or accessible with data that's already public. And so that seems like a rich field already for a lot of papers about what's happening with the host halos and the stellar masses of these early galaxies.
Okay, so thank you very much, Peter. So let's thank Peter again.